Yes.
Hello, everyone. Can you hear me?
Yes, sir. So, chair for the session, Professor Prabal Choudhury has joined us. So, let me start the recording and we'll be starting our proceedings. Okay, so welcome all to the second plenary lecture of the Winter School on Deep Learning 2023. We have two very special people amongst us today, both pioneering researchers in their respective fields and masters of their craft. Their lives' work have inspired many and continue to shape the future of learning theory and statistical research in general. It is my great pleasure to announce today's plenary speaker, Professor Gerard Biau, and the session chair, our very own Professor Prabal Choudhury. On behalf of the whole team of WSDL 2023, I sincerely thank you both for agreeing to be with us. It is our great pleasure to have you on board our endeavor, that is the Winter School. So let me introduce the chair for this session first. We all know him, one of our most beloved professors of Indian Statistical Institute, Kolkata, Dr. Prabal Choudhury. He has been a full professor at the institute since 1997, after joining in the year 1990. He also calls ISI his alma mater, where he completed his bachelor's and master's degrees from. And Professor Choudhury got his PhD in statistics from the University of California, Berkeley in 1988. I won't be able to fit all his accolades in the short while I have been spared, but I will only mention remarkable few. He is an elected fellow of the Indian Academy of Sciences, Indian National Science Academy, and the Institute of Mathematical Statistics, amongst many. He was presented the Shanti Swarup Bhatnagar Award of CSIR in Mathematical Sciences in 2005 for his contributions in the field. Professor Choudhury is also the recipient of the National Award in Statistics in honor of Dr. C.R. Rao, awarded by the Ministry of Statistics and Progress, Government of India, the same year also. You may also know him for his seminal work on geometric notion of quantiles for multivariate data, quantile regression trees, and data depth, to name a few. So without any further ado, I would request Professor Choudhury to introduce our plenary speaker and say a few words as a note of welcome. Sir, the stage is yours.
Thank you, Anish, and thank you for inviting me to this session for chairing. I hope I am audible to everyone. Anish, am I audible clearly?
Yes, sir. Yes, sir.
Okay. So it's an honor to chair a session where Professor Gerard Biau will be speaking. I don't know him personally, but I'm familiar with his work, and so I mean he is a stalwart in his own area. But probably many of you already know about him. But nevertheless, it's my pleasant duty to introduce him for the audience. So I will do that. So Professor Gerard Biau is a professor at the Probability, Statistics and Modeling Laboratory of Sorbonne University, Paris, where he acted as the deputy director from 2018 to 2021. He was a member of the Institut Universitaire de France from 2012 to 2017 and served from 2015 to 2018 as the president of the French Statistical Society. In 2018, he was awarded the Michel Monpetit Inria Prize by the French Academy of Sciences. He is currently the director of the Sorbonne Center for Artificial Intelligence his seminal works on the theoretical properties of GAN, which is the abbreviation for, I think it is, I'm not quite familiar with this term. It's probably a generalized adversary network, or am I correct, Anish?
Yes, sir.
Generative.
Yeah, generative adversary network. Okay, because I'm not, though Anish said so, I'm not really an expert on statistical learning. It's true that some of my work has been picked up by statistical learning community and they have used it, but I'm not an expert in that area. Anyway, so his seminal work on the theoretical properties of generative adversary networks and consistency analysis of random forests have transformed the course of statistical research in machine learning. Among his various editorial responsibilities, notably, Professor Biau served as the associate editor of the Journal of the American Statistical Association, Biometrica, and the Annals of Statistics, which are, in our field of statistics, three topmost journals. Okay, so it's like, I mean, when we were PhD students, it's like if we have one paper in any of these three journals, we'll be celebrating. So I will not say anything more, and I will leave the stage to Professor Biau. So Professor Biau, the stage is yours now.
Thank you very much, Professor Chaudhuri. I mean, I don't deserve all these nice words, so thank you very, very much. So thank you very much, Anish. Thank you very much, Swagatam, for this very kind invitation. It's my great pleasure to give this talk for the Winter School. And so it's Sunday in France, so it's very quiet. I'm at home, so I have plenty of time. So I'll be very happy to discuss with the students after the presentation. So just let me prepare everything there. Oops. All right. So the title of this presentation is Scaling ResNets in the Large Depth Regime. And as you will see, it's a sort of mixture between statistics, machine learning, and also probability theory. And this is a kind of research that I like very much because it's sort of a mixture of very different fields, and I think it's interesting. So I have a team in order to implement this research. So this is the team for the present paper. On the left, you can see Adeline. So Adeline was my former PhD student. She's now joining a company. She was as a postdoc at l'École des Mines in Paris. Now she's joining since 2 days ago a company in France, a machine learning company. Pierre Marion is a PhD student of mine at Sorbonne University. And Jean-Philippe Vert, he's a colleague. He was during the preparation of this paper at Google Research in Paris, and is right now in a company which is called Okin, which is a company which is doing machine learning for health and healthcare. So thank you very much to all. So that's the agenda for today. First, I will try to explain you what these ResNets are and why it is interesting to study them and what's exactly the problem with this type of ResNets. So ResNets means residual networks. And as we will see, they are quite unstable, and there is a big issue with these ResNets, which is the initialization before we launch some optimization process to find the exact weights. So that's the question that we will discuss in the first part of the presentation. Then I will show you how to scale these these deep ResNets in order to make them more stable. That's a very important question, and we'll try to answer this question in the second part of the presentation. And then we will see that, very interestingly, these deep networks can in fact be understood as sort of discretizations of a continuous differential equation. And that's the main message of my presentation. The main message of my presentation is that very deep networks, some very deep networks, can be understood as discretized continuous phenomena such as partial differential equation or stochastic differential equations. That's what we will discuss in this third part. And finally, I will present you some experiences that go beyond the initialization step. This is not supported by any theory, but I will show you some experiences to prove you that there is a lot of things to be done in the field. Okay, so let's start with ResNets, or with residual networks. So my main presentation will be about supervised learning. So that's how most people see the supervised learning problem. And you have a bunch of images, and these images, they can be cat, or they can be dog, or they can be whatever. And the machine is given a lot of samples, which are already labeled. And then you fit an algorithm. And of course, you may want to decide if a new image is a dog, a cat, or whatever you like. So that's essentially how most people see the supervised learning problem. And in particular here, it's a supervised classification problem. So, of course, it's not enough for mathematicians. And if we look on the computer science side, then that's essentially how machine learners see the supervised learning problem. So I think it's very interesting. It's a great source of problems and aspiration for mathematicians, but it's still not quite satisfactory because, of course, as statisticians, as mathematicians, what we have to do is to try to extract the main principle, the main models of all these very nice ideas. And so that's where my research really is located. It's at the interface of this kind of algorithms of figures and math. So from the mathematical point of view, that's how we statisticians see the supervised learning problem. So the goal is to understand the connection, the relation between some input random variable, x, which is living in a space r to the n in, and an output y, which is living in another space r to the n out. And of course, they are both random, and what we want to find is the connection between these two random variables using samples, which are just repetitions, RID repetitions of the initial random variable xy. So that's what we have at hand. And of course, to do that, we assume that we have at hand a model. We call the functions npi. So pi is a sort of parameter, if you want. And of course, these are functions, and they start in r to the n in, and they land in r to the n out. And in our case, these collections of models will be ResNets. And the pi will be the weights that we put on the neural networks. And of course, pi can be extremely large. And in modern machine learning algorithms, this goes to several billions of parameters. Of course, having npi is not enough. And what we have to have is a loss function. And this loss function measures what we lose when we use npi to predict y. So that's the difference between reality and what is predicted. So for example, if we perform regression analysis, then the loss between what we predict and what we see, so L between npi of x and y, is just the square values, the square distance between y and npi of x, assuming that everything lands in R. Of course, there are many different possibilities. For example, if you perform classification, in classification, supervised classification, what you aim to do is just to decide whether y is 1 or 0, if you have a cat or a dog, say, to make things simple. And in that case, if npi is positive, then we decide that that the decision is 1. And if npi is negative, then we say that the decision is going to be -1. So cat versus dog. And of course, we make a mistake if y and npi are of different sign. And so the loss function in that case is going to be the indicator of the sign y npi is less than 0, is negative. So of course, there are many, many different possibilities. Of course, the indicator here can be smooth, etc. You can have multivariate outputs. So it won't be a big issue in this presentation, but I just want you to keep in mind that that's the general context. Then once you have your loss function, your model, then of course you have a best parameter, which is called here pi star, and which is just the guy in pi is there. That minimizes this capital L of pi, which is called the theoretical risk. So that's just the expectation of the loss between what we predict and y. And of course, the expectation is with respect to the distribution of xy. And this parameter is the best one since it just minimizes on average the prediction between the difference between the prediction and reality. Of course, in practice, you cannot use this parameter P star just because the distribution of xy is unknown, and so the expectation itself cannot be computed. And so what we do is just that we replace the theoretical expectation by the empirical expectation. So instead of pi star, we use pi n, which is the minimum not of this L, this capital L here, but of Ln, which is just the empirical averages over the sample of the differences between the m pi of xi and yi computed with L. And of course, this can be computed. And usually as statisticians, what we say is that, well, we have this pi n, which is the minimum of the empirical risk. And of course, if you are more a machine learner, if you are more interested in optimization problems, then you have to find an algorithm in order to find this pi n or something which approximates well this pi n. And that's a big issue, of course, because as I said before, pi can be a very, very, very large dimensional set. And of course, then you have to implement some gradient descent algorithms, some stochastic gradient descent algorithms, etc., in order to approach the best parameter pi n. That's a question that I won't touch in my presentation, but I just want you to keep in mind that this is a very important issue in machine learning. Okay, so that's the general framework. Then, of course, if we want to go further, then we have to define the type of model we are working with. And in this presentation, I want to advocate the use of a model which is very important in machine learning. And these models, they are called, or the elements of this model are called ResNets. So how does a ResNet work? So ResNet stands for residual neural network or residual neural networks, if you speak of ResNets. So the idea is the following one. So capital L here is the depth of the network. So when we speak about deep learning, so you should think at capital L, an integer which is larger than 1 and which is big. So capital L is the depth, and you define a sequence of hidden states, H0, H capital L, and they are defined by recurrence as follows. So first you have your data X, it's there, and you transform X by some matrix A, and so you land in R to the D, fine. Then you have a sequence of HK, H1, H2, H3, etc. And you pass from HK to HK plus 1 by adding to HK some function F of HK, so the current state, comma, a parameter which is unknown, and of course, which has to be fitted. You do this capital L times, and once you have done this capital L times, then you want to land in the output space, and so you remultiply the output by some matrix B, and this is m pi. So you see that what is unknown there, it's the initial matrix A, the final matrix B, and of course, all these mechanisms there, where there are many, many parameters, theta 1, theta 2, theta capital L. Of course, what we are going to do is to make precise what is this function F here. But before that, I want you to observe that there is this HK here. So we pass from HK to HK plus 1 by adding to the current state HK some function F. And so this connection here is called the skip connection. And it plays a very important role in the analysis, and I will explain why a little bit later. So of course, now, if we want to go further, we have to specify the form of this function F, which is a function that takes two arguments. And the first one is the current state, and that's living R to the D. And the second one is the space of parameters, that's living R to the P. And of course, that lands in R to the D. And of course, different forms for this function F leads to different architectures of ResNet. So there are not one single architecture for ResNet, but the general model is the following one. So what are the different possibilities for this function F? Well, in the original ResNet paper, that's the function that the authors take. It's there. So you see, it's quite easy. If you are familiar with fully connected feed-forward neural networks, then of course you know this this kind of function. So how do we pass from HK to HK plus 1? So we have HK, we multiply HK by some matrices, some matrix WK plus 1. So it's a big matrix, right? If D is large, then it's a D times D matrix. Then we had eventually an offset B, that's a vector. We take the Rayleigh function, so Rayleigh, it's an activation function. So here, Rayleigh, it's a maximum between X and 0 of all the coordinates of the output. And then eventually we remultiply behind by some matrix V. The coefficients of this matrix are known. And that's the function F. And of course, we have computed F, we add HK, and then we get HK plus 1. And then we play this game again and again and again, all over the layers of the neural network. So what is unknown in this business? Well, of course, as I said before, A, the first matrix, B, the last matrix, and all the V, W, and B. And there are many of them. If capital L is large, of course, then you have many of parameters to which are unknown and which define the neural net. So you see, it's A, B, and all the theta K, which in the theta K is a collection of V, W, and B. And you see this in the original paper where they first implemented this architecture with this HK here. That's the way computer scientists or machine learners usually represent the addition of F to HK. So just before I go there, for us to be online, so here that's R to the in. Then I multiply by this matrix A. I land in R to the D, and then these are my layers. I have capital L layers, so capital L in this presentation is going to be very large. And then we pass from HK to HK plus 1 by adding the previous state to the function, and then we pass using these different functions F from one layer to another. So, right? So this is H0, H1, H2, HL, and in the end, we multiply by B, and we have the output. So that's a possible architecture. So let me go back here. So that's the original ResNet. But of course, you may replace the Rayleigh activation there by something which is smoother. This is sometimes called parametric ResNet. This is exactly the same architecture, but except that you replace Rayleigh by something which is smoother, for example, arctangent function. And this is sigma computed over all components of the vectors. This is component-wise. You may simplify it a little bit. That's a very interesting model, which is called simple ResNet. So in that case, you see that you take this HK, you compute the activation of all the HK, then you multiply your matrix V, and you do this capital L times. So it's a simpler model. In that case, the parameters are, of course, A and B, beginning of the process, end of the process, and then all the theta K, this matrix V. And in full generality, well, a general ResNet has the following form. It's V matrix times a function J of HK, the current state, and the parameter W. So that's a general ResNet. But of course, if you want to keep in mind something simple, just keep in mind this model here, and that's more than enough. Okay, so these are different architectures. There are others, but the important point to keep in mind is the following figure, where we pass from the entry of the network to the output of the network by a succession of layers. The depth is capital L, and the network, they are quite shallow in the sense that all the layers have the same width. It's R to the D, and so that won't go to infinity. The parameter which is going to go to infinity, and that's of course a different point of view than traditional, traditional statistical point of view, which usually assumes capital L fixed and D goes to infinity. In this presentation, it's a talk about deep learning. Yeah? Capital L is going to go to infinity and D is going to be fixed, right? So R to the in matrix, we have the sigma, and then we do the sigma, another matrix multiplication, sigma matrix multiplication, sigma, etc. But importantly, we have the previous state each time we perform an operation, and that's the signature of ResNet. So why are these ResNets so important? Well, there was a revolution with these ResNets that happened in 2012, 2013. And this revolution happened in the context of a competition, which is called the ImageNet competition. And this competition was organized by an association from 2010, 2017, I guess. And the goal was quite simple. The idea was to use a database, which is also called the ImageNet database, which is a very complete database with classification task to accomplish. And the best teams won the award of the competition. And this challenge really helped to push the state of the art in deep learning. So you see here, when the competition started in 2010, people essentially use shallow networks. I mean, shallow network, I mean, old style neural networks. In the sense of this network, they were not very deep. So in our case, capital L small, but they were shallow. So old networks, I would say, in the sense that D, right, the width is large. So they perform quite well, 28% of error, 26. And then there was a sort of revolution in 2012, 2013, when new architectures with more layers, deeper networks started to appear. And then, of course, there was a big gain in the classification accuracy, 16%, 12% was networks such as AlexNet, ZF, etc. But then there was, again, a breakthrough that was in 2015, so 7 years ago, when the ResNet type architectures were introduced, and that was the first time that really deep networks could be implemented. And now you see that there was a jump in the error from 6 to 3, and with this ResNet, that was the first time that really deep networks could be implemented. And you see that we could jump, we jump at this period from 22 layers, so capital L is 22 to capital S 150. And so this ResNet they really play an important role in deep learning. And you see that today, where there is no more evolution, we are just below the human error. Well, we do better than human error, and that's kind of stable around 3%. So this ResNet, I think they deserve some attention because they have something special. And today, of course, you know that deep nets, they have up to much more than 100 parameters. You can up to 1,000 parameters without problem. So the question is, what is the connection exactly between this ResNet style networks and deep learning? I mean, why is it so important to have this skip connection? Does it play a role? Why are these ResNets so special? So that's the main goal of my presentation, try to understand this better. So before this, some of you have probably noticed already the connection between these ResNet and differential equations somehow, because you feel it immediately. When you see a ResNet there, you feel that resembles what you saw in your course of differential equation. It looks like the discretization of a differential equation. You see, everything is there. You pass from hk to hk plus 1 by adding some function f. Okay, you see, well, we should add something before the f, but okay, it looks like the discretization of some differential equation, and that has been observed already 2 years ago. So I think it's important to have this in mind, because that will be the main message of my presentation. So for traditional neural networks, let's say for feed-forward neural networks, there is no skip connection hk. You pass from hk to hk plus 1 just by accumulating layers. That's what happens with a feed-forward neural network. With residual neural network, you have this hk here. And as I said before, it resembles a discrete version of a differential equation. And we immediately want to put a 1 over L here. So capital L is the depth of the network. And if we have this, well, this is the Euler discretization of a differential equation. And of course, this has been observed in 2018 by Chen and collaborators. That was the best paper at NeurIPS. And these people said that, well, in fact, ResNet is just a discrete version of differential equations. And so the shift of paradigm there is that the K, which is the discrete numbers, which is the number of layers, is understood as a discrete version of time. And so the mechanism which is behind the neural net is in fact a continuous time mechanism, which is there. And this type of equations is called a neural ordinary differential equation. So the main idea is that instead of looking at your network layer by layer, you look it over a sort of continuous time over the layers. And the layers, they are just particular instance of time of something which is continuous. And so there is a sort of junction between two words, which is happening now. The world of deep learning, of networks on the one hand, and the world of ordinary differential equations, of differential equations in general on the other hand. And this makes a field which is called neural ODE, neural ordinary differential equations, or neural differential equations. And why is it interesting? It's interesting for several reasons. The first reason is that, of course, by seeing a neural network as the realization of something, as the discrete realization of something which is continuous, then we can propose new architectures. We can use solvers of differential equations in order to find the parameters of the neural net. And of course, the theory of differential equation is much older than the theory of neural networks. So there are many, many interesting tools for stability of the networks, for how to initialize the network, for the existence of solution of the differential equation, etc. And all these tools, they can be used, reused in order to analyze the mathematics of the neural network. So that's a very interesting field of research, which is quite new. And in fact, this participates of a general movement of convergence between the world of differential equations and machine learning. And you maybe heard about this physics and form type neural networks. So that's in this spirit. And so there are some papers, which mixes both, here the Runge-Kutta networks with new architectures of neural networks inspired by what is done in the field of differential equations, antisymmetric networks, new architectures, again, that use tools, architectures, ideas from differential equation fields in order to craft different neural networks. So just to summarize this introduction, on the left, you have a ResNet, so the type of network that I'm going to use with this 1 over L before, right? So A, B, this here, this scaling here 1 over L in order to make it resemble differential equation, and to the right, the neural ordinary differential equation, and with the function f, which in the more general case is a V matrix, sigma matrix A times H plus B. And so that's the way most people see these deep networks, but as we will see, it is not fully satisfactory because this 1 over L here is not so neutral, and that's what I'm going to discuss in the very few minutes. But that's the general context. And just one word of warning: maybe you heard about not ResNet but recurrent neural network (RNN). So I don't know how you are familiar with this architecture. So it's something different. RNN, so recurrent neural networks, they are here more to handle observations which have a temporal structure, typically time series, or observations which evolve over time. And it's a little bit different. You may also incorporate in the residual neural network a skip connection. That's also possible, but they are different in the principle. So if you are interested in RNN, so there is this paper that we published in Europe 1 year ago. We tried also to make the math quite clear on the recurrent neural networks. But I just wanted to advise the fact that when I'm speaking about ResNet, I'm not speaking about RNN. Okay, so far so good. So that's where we are. Now, what about scaling these deep ResNets? In fact, these ResNets architectures, if you really want to use them in a large depth regime with a capital which is large, then you have to be very careful in the way you train these networks. So what do I mean by training a network? When capital L is large, then there are all these parameters in the matrix W, B, theta, etc. And you have to find the best parameters. So what people usually do is that you start with some initialization of these parameters. Usually it's a random initialization. You take IID Gaussian, for example. So you put everything independent, where independent weights everywhere with some initializations. So Gaussian random variable, say. And then you start a gradient descent, right? Trying to tune to find the best parameter. But even the initialization is complicated, as I'm going to show you here. So let's take an original ResNet. So that's a model, exactly the type of model that I presented you before, you know, with capital L layers. And we pass from one layer to the other by this iteration there. And so let's start initializing the network with matrices A, B, V, and W. And we tell all these matrices are RID realization of Gaussian points, right? So all the components are independent, they are Gaussian, and we look very simple. Once we have simulated all the weights, the weights are there. We have a network, and we can use this network. Of course, that's initialization. It's not a very interesting network in the sense that the weights are not tuned, but anyhow they are here. And here, what's happening if you do this? If you, that capital L is the depth of the network. So I took a network from depth 1 to 100. And I look at the norm of the output of the network. So HL is the norm of the last layer. So that's the vector, which is used for prediction if you want. And I compare it to the norm of the H0, which is the norm of the first layer. So I don't see if you see the details, but for each capital L, I repeated 50 times the experiments. And what you see here, the curve in blue is just the average. And what you observed is that each experiment is with a different initialization, of course. And nothing is learned there. It's a very it's a frozen network. And you see that when the depth, capital L, grows, then the norm of HL, well, just become extremely big. So there is a problem. There is a problem, of course, because this means that if you initialize a network with random weights, and you use this network, this initial network, well, that's a network, it is random, that's a network, with a lot of layers, then the output is going to explode. And of course, you immediately feel that if you use this type of networks as initialization for an optimization process, then it's going to do a very bad job because your network just predicts something which is infinite. And the gradients are going to be hopeful to compute, etc. So there is something to be done. There is something missing there. And people know that. And usually this problem is solved by using a sort of normalization. And so there are two solutions which are used for this. The first solution is called batch normalization. I won't speak about that today in my presentation. So batch normalization is layer after layer, you add some kind of normalization of using the data, or scaling. And this is what I'm going to speak about today. So what is scaling? Scaling is the idea of adding a parameter before we do the iteration to pass from one layer to another one. And this scaling factor has the form 1 over L, so the depth of the network, to the power beta. And of course, it makes things a little bit different because when capital L is large, then 1 over L to the beta is going to be small, etc. And so the question, the very important question is how to choose this beta. It's an essential question. It's a very important question because if you take, well, nothing, if you take beta equals to 0, then we have seen that the network is just exploding, right? You just have a function which is infinite, basically. So how do we choose beta? 0, it's not a good solution. Again, it predicts infinity. Should we choose beta is 1? Well, it's, you know, as I said in the first part of my presentation, if we choose beta equals to 1, then immediately resembles an ordinary differential equation. Is it a good regime? Does it work? Question. Or should we choose something different? So there are many empirical studies on this beta, on the chart of this beta, and there is no consensus at all in the literature. And again, it's a very important question because if your network, again, at initialization, just predict something which is infinite, then you are going to get in trouble when you are going to train it. So in this presentation, well, we are going to do some math and trying to see if the math can tell us something about the best choice of this beta. And again, the approach would be, I insist on that, at initialization. So there is no optimization process. I'm looking at the network at the beginning. So everything is summarized in the following picture. So what did I do here? Here, capital L is the depth of the network. So I take a network from depth 1 to 1000, right? And here I look at what's happening in the output of my networks with RID initialization. So each point is an experience. So there are many of them, they're average. And I look at the output. And you see that if beta is 1, you see that the output of the network, so that's the difference between the output and the input. It's close to 0. So it means that in that case, if you take beta large, beta 1, then the network essentially reproduces the identity. Fine. On the other hand, if you take beta too small, then we are in this case of explosion. Then the network explodes. And finally, if we take beta 1/2, so it's 1/square root of capital L, then there seems to be some kind of random fluctuation of the output. So it's a totally different phenomena. You see, we have 3 very different regimes there. And the good scaling seems to be 1/2, because in that case, there is an explosion of the networks. So my function is infinite. Here, my function looks like the identity function, which is not exactly what I want. I don't want to, I don't want to use a network with 1,000 parameters, 1,000 layers, millions of parameters in order to just to encode the identity function. So it seems that this type of parameter beta 1/2 is much better for learning. The same results, the same triptych, identity, explosion, say stability, is also true for the gradients. So that means the derivative of the loss with respect to the parameters, and we'll come back on this later. And what is very strange is that the good scaling, 1/2, is not the ODE scaling. As I said before, well, it seems that beta is 1 is fine because it makes the network resembles a differential equation. So of course, that's a very strong argument to say that the good scaling is beta is 1/L. But I mean, it seems that not, and that the good scaling is 1/2, 1/0.5. So this is supported by the following theorem, which say the following. So assume that the weight of the network are initialized with random points, so symmetric RID sub-Gaussian, so typically uniform random variables, Gaussian random variables, and many others. So D is just the width of the layers, and all the weights, they are independent. RID initialization, and that's usually what the solvers do. Most solvers use this type of initialization. And so there are 3 regimes. If beta is large, then we can prove that in probability the difference between the output of the network and the input of the networks goes to 0. So it's a sort of identity reproduction. On the other hand, if beta is too small, then we have explosion in probability. And if beta is 1/2, which is seems to be the critical regime, in that case, we prove that with large probability, then we have a random fluctuation between 2 bounds of HL minus H0 to the square, so divided by the input of the networks. But the important message here is that there is a fluctuation. We don't, unfortunately, proving this kind of theorem is complicated because we have to use concentration inequalities for martingales, because of course the structure of the network makes you end up with a martingale. And we don't have exact distribution, we have bounds, but it's already there. It's already something. It's already a message that we have 3 regimes. So as I said, exactly the same can be done for the gradients, because usually computer scientists are more interested by the gradients than by the output. So what is the gradient? So the gradient is the derivative of the loss with respect to the weight at each hidden state. And so in that case, so I don't want to enter the details, but when you write the equations for of the gradient of the networks to perform the gradient descent, then what matters is the forward pass. I mean, the gradient, when you start with the gradient in the end, and you want to look at the gradient at the beginning. So what matters in that case is P0 minus PL, the value of the gradients at the beginning of the networks minus the value of the gradient. What is given is the value of the gradient in the end. And in that case, the gradient back propagates in the other way, in the sense that the order is not natural. If you want, you have no equation to pass from pk to pk plus 1, but you have an equation to pass from pk plus 1 to pk. And so pk is the gradient, the derivative of the loss with respect to hk. And of course, it's very boring. It's very boring because that's the wrong way. You have no martingale structures. Everything depends on everything. So it's impossible to perform math on that because you have no structure of the equation again. And so the idea, so I don't want to be too technical, so that's not the idea of the presentation, is instead of looking at pk, we look at the derivative of hk with respect to h0. So that's the matrix of all the derivatives times some vector z, and so that's a vector. And in that case, if you multiply this matrix of derivatives by a vector, then we have a good flow of information in the sense that we can pass from qk to qk plus 1 in the order of time by an equation. And that's this equation that we use. And once we have done this, we end up with QL. We are able to provide some information on QL. And then the question is how to pass from QL to P0, because that's what we want. So the gradient at the beginning of the networks, and use this kind of trick, taking that the expectation. If you take Z Gaussian, then P0 to the square is just the expectation with respect to some Gaussian random variables of QL times some coefficient. So that's the general idea. I don't want to bore you to annoy you with details, but anyhow, my message that we can prove exactly the same type of results for the gradient. So it's not something which is specific to the output. And by the way, this is also confirmed by the experience. You see here the difference of the gradients of the networks when capital L goes large. If beta is large, then again the gradient just, there is no movement of the gradient when you pass from the end to the beginning. So identity. When beta is too small, explosion, exactly the same. And on the other hand, when beta is 1/2, then there is a random fluctuation of the gradient, which of course looks better if you want to learn something on your network. So this is summarized in the following theorem. So again, if the entries of the networks are IID, and again, this is this type of initialization which is commonly used by the softwares, then we have three regimes. Identity, that's for the gradient, exactly as for the output. In expectation, you have explosion. So it's a little bit weaker here for the gradients, and the questions are a little bit more complicated. And again, sort of random fluctuations. Here we have bounds in expectation between two values of the expectation between the square norm between P0 minus PL to the square. And it's a sort of stability here of the gradient. So the message is that for the output of the networks or for the gradients, if you use a random initialization of your networks, then you have really three different behaviors of your neural networks: identity, explosion, stability. You may ask, do we have some information regarding the distribution of the output of the network when capital L goes large? Well, I think it's a very interesting question, a difficult question. It seems to be log normal, but I'm not sure of that. Yeah? You see that the distribution over many, many different repetitions of the norm of HL, and here that's the norm of the gradient. Okay, this is normalized by H0, and this guy, they are assumed to be constant. Huh? And it looks like log normal, but well, I think it's a challenging question to have the exact distribution. What we have is bounds. And the quantiles, and the quantiles of this distribution are matching the bounds. So it seems that the bounds that we have are quite sharp. But again, we have no proof of that we have an exact distribution. So now there is a question: where does this value 1/2, which seems to be so important, comes from? So if we take a step back, then we see that, let's have a look at a simple ResNet with this 1/√L normalization, which is to be the ghost one. And then we pass from HK to HK plus 1 by adding 1/√L to this function there, V, the matrix times sigma. And this is this V, which is randomly initialized and with RID observations. So the entries are RID of all the VKs, Gaussian, with a variance 1 over D, 1 over D. This is exactly the conditions of my theorem. And look, denote by B, a D times D dimensional Brownian motion. So you know that the Brownian motion is it's a Gaussian process with independent increments, and the increments are Gaussian. And a D times D Brownian motion just means that I have a big matrix with independent Brownian motion, one-dimensional Brownian motion. And you know that if you look at the increments, so AJ is just an index for the matrix, line A colon J. And if you look at B for fixed AJ, the difference between K plus 1 over L and BK over L, so that's the discretization of my Brownian motion over the grid 1 over L, then it's normal with variance 1 over capital L. And that's in your course of, in your probability course. But then it's interesting, of course, because this means that you can rewrite, at least in distribution, you can rewrite this iteration as the following iteration. So what is this? So forget about the transpose, they are just here because for the good, you know, the good way of multiplying matrices, but that doesn't mean anything. So you pass from HK to HK plus 1 just by adding sigma of HK, so the sigma is exactly the same. But of course, since this guy here is made of independent Gaussian random variables, then it's exactly the same as multiplying by the difference of these two matrices there, because they also behave as independent Gaussian. That's the same. And of course, we multiply by, so the 1 over square root of L disappear because it's included in the difference there, because it's Gaussian 1 over L. And the 1 over square root of D is just because we have a D times D matrix. So in distribution, it's exactly the same iteration. But then it's interesting. It's very interesting because if you're familiar with this, then here you recognize what is called the Euler-Maruyama discretization of a stochastic differential equation. So what I'm saying there is that a ResNet with this normalization 1 over square root of L, with weights which are independent Gaussian, in fact, behaves as the discretization of a stochastic differential equation, not an ordinary differential equation. So now we have to change the 1 over L into 1 over square root of L, which is the good normalization. And you see that on the right, you pass from the discrete to the continuous world here, but here you have a stochastic differential equation. So it's called a neural stochastic differential equation, and definitely not an ordinary differential equation. So this can be made more precise. So again, assuming that the entries are Gaussian, and that sigma here, the activation is Lipschitz continuous, which is fine. This is true for any kind of, for all the traditional activations. Then we can prove that the following stochastic differential equation has a unique solution H. And moreover, the difference between the discretization of this differential equation and the values of my networks H1, H2, HK, well, they are very close, and in expectation, they are close up to a parameter 1 over square root of L. So this is a very interesting message. This means that with this normalization 1 over square root of L, if you initialize the networks with random weights, then it behaves as the discretization of a very simple diffusion model, which is a stochastic differential equation of this type there, and not an ordinary differential equation. And of course, this opens the door to many different analysis, of course, for optimizing the network, for understanding the way they behave, etc. So the surprise there is that you end up with a stochastic differential equation and not a differential equation. So to summarize so far, what we have seen is that if you initialize your network with RID observations, then the critical value for scaling is 1 over 2, not 1. And this limit corresponds when capital L goes large. And look here, if capital L becomes, when the depth of the network goes to infinity, then these two terms, they crunch. And so it just means that your network is in fact a stochastic differential equation. Then in the D limit, you obtain a stochastic differential equation. So there are, of course, remaining questions. Can we obtain all the limits? For example, ODEs. Is it possible or not to work with beta is 1, with different normalization? And do they correspond to the same critical value? And it turns out that the answer is yes. But if we want to go further, if we want to use different normalization for the neural network, then we have to change the distribution of the weight. What is clear is that there is a sort of intimate connection between the scaling and the type of distribution that we are putting on the weight. What I said here until now is that with beta is 1/2, then this matches the case where you use random initialization of your network. Now, if you want to use a different sort of beta, say beta is 1 to have an ordinary differential equation, then you will have to change the distribution of the weight. So let's see how. The key is to understand the connection between beta and the weight distribution. But wait, what does that mean, the weight distribution? If you have the weight of your network, so the values of the matrices, the initialization is fine. But what is a different distribution over the weight? How should we model it? With correlations? With what? So the key here is to get deeper into the analysis and, in fact, to see the weight of the networks as a discretization of a continuous function. And this function here, it can be a process and it can be extremely regular. And so we can have like this a bunch of regularities to initialize the weight. So, but for this, we have to delve into something which is a little bit harder. And it's the continuous world. We have to understand, we have to jump into the world of stochastic processes. So let's do it gently. And we leave the ID world behind, and we look at the general resonant model like this, the discrete model. The main ID, if you want to use this 1/L, not 1/square root of L, if you want to use this 1/L, is to change the distribution of the weights. And to do this, we are going to assume that the weights, so they are the V, the W, they are in fact discretizations of smooth functions. So this means that I assume that I have somewhere a function V like this, and the V case, they are discretization of this function V. Same thing for the W here. And of course, I'm going to assume that this function V and W, they are smooth in the sense they are random, that they are stochastic processes which are typically Lipschitz continuous and bounded. So understand what I'm doing here. I'm just saying that if you follow a weight of the networks over the different layers, then in fact, it's a discretization of a function, of a process, which is very regular. This process can be, for example, a Gaussian process with zero expectation and exponential covariance, for example. But you can take what you want. I mean, it's something which is regular. So this is summarized on the following figure. So in the first part of my presentation, all the weights here that you put on the arrows, they were ID. Now there is some structure. If you follow one weight, so let's take this weight here. That's the weight which connects the first layer to the second that way here. It's the same weight, and you follow the weights over the layers. I'm just saying that this weight is the discretization of a function which is very regular, and that's the same for all the other weights, and you have plenty of these weights, of course, right? So it's a point of view, but it's a very legal point of view in the sense that I can initialize my networks by taking the discretization of processes which are continuous. It's not, I mean, it's perfectly fine. You take a Gaussian process that you just, with some covariance function, that you just discretize, and then you have initialization of the networks that way. That's perfectly fine, practically fine. So it makes a big difference. So that's if you follow one weight over the layers, So that's an ID initialization. There is no connection when you pass from one layer to another one. If you use something in initialization which is smooth, then you have a lot of connections between the value of the weight at layer L, at layer small l, and the value of the layers at layer, and the value of the weight at layer L+1, of course. So there is a lot of structure. It's very, very different. But again, it's perfectly fine. You can do this in practice. And in that case, with this 1/L normalization, with this type of assumptions on the weight, then you have a neural ordinary differential equation. And this can be formally proved if the function J is Lipschitz continuous. But again, that's for general ResNets. That works for all kind of ResNet that I presented you before. Then again, the theory tells you that there is a unique solution H to the differential equation. That's the so-called Picard-Lindelhoff theorem. And moreover, your network is just the discretized version of this ordinary differential equation. So it means that working with 1/L is perfectly fine, but you have to change the distribution of the weights and use something which is much smoother in order to have a neural ordinary differential equation. So now you may ask the question, well, but is it still true that if you are in the ODE regime, ordinary differential equation regime, that the scaling that there is this critical regime with the scaling above and below 1? Yes, it's perfectly fine. Then the simulation they show it very clearly. If you take beta too large, then when capital L becomes large, then you just reproduce the identity. On the other hand, if beta is small, then you have an explosion. And when beta is 1, then you have a random fluctuation. It's quite hard to prove. But what is interesting is that you have 3 cases: identity, explosion, stability. And now the scaling, I mean, the critical scaling is 1, not 1/2. But again, this is connected to the fact that we have changed the distribution of the weights on the network. So if you're interested in the theorem, so if W and V and W are Lipschitz continuous and bounded, so these are the function that model the weights. Then you have 3 regimes. Identity, so we have a normal share result there. It's much harder to prove, of course, because it's you have to use a tool from stochastic calculus. Sorry, it's from not from stochastic calculus, from continuous processes. Stability for beta is 1, and if beta is small, then we have explosion, but we have to ask some more assumptions here in order to have some explosion. So the results are harder to prove, but the ideas are there. You have these three regimes again, and then of course this is totally in line with the observations. Okay. Now there is an immediate question that you could ask. You could say, well, you have proved that when you have RID initialization, then the good scaling is 1/2, and it's a stochastic differential equation. You have proved that when you have very, very smooth initialization, then the good critical scaling is 1, and in that case, you have an ODE. But is that possible to have some sort of intermediary regimes, transitions between the very irregular case and the smooth cases? Is that possible to pass from one regime to another one? So the answer is yes. And a possible solution for this is to initialize the weights of the networks as increments of what is called a fractional Brownian motion. So what is a fractional Brownian motion? Well, it's a Gaussian process which has a very particular structure of covariance. It's there. And it's very interesting because it has an index here, which is called the Hurst index, H. And if H, it lives between 0 and 1. And if H is 1/2, then it's a traditional Brownian motion. And we know that if we take the increments of a traditional Brownian motion, then we have the ID regime. When H goes to 1, then it's something which is linear. And that's fine, of course, because we know that if we take the increment of something which is linear, then we end up with something which is very regular. And so we are in the smooth case. And when h goes between 1/2 and 1, then we have a bunch of intermediary regimes. You see? So here it's 1/2. The increments are then the increments. So sorry, that's a Brownian motion. When h goes to 1, it becomes linear. And when h is small, it's very, very aggressive, very irregular. So this is a good way to model the transition between the RID world and the continuous world. h1/2, we have the standard Brownian motion, SDE regime. When h is smaller than 1/2, the increments are negatively correlated. That's there, very aggressive process. And when h is larger than 1/2, then the increments become positively correlated. And when h goes to 1, where you see you have this type of linear behavior. And that's the ODE regime. And when h goes between 1/2 and 1, then we have a bunch of intermediary regimes. So the challenging question is, can we have some results for all these type of intermediary regimes? So everything is summarized in this figure here. I have no mathematical proof. It's more prospective, but I think it's very interesting. So look, here you have the regularity of the fractional Brownian motion, the h. So when h equals 1/2, so we take the increments of this process, and so these are the increments of a Brownian motion. So that's the RID case. Here you take the increments of something which is linear, so that's the smooth case. So here you see that's what we call the SDE regime, and here that's what we call the ODE regime. And here you have the scaling. So what did we do there? We did that for each pixel. It means for each per regularity scaling, we look at the output of the network. And when it's black, it's fine. When it's blue, it's small. And when it's red, it's big. So let's take the ODE regime that we have already studied. So we have the RID regime here. We see that if we initialize with scaling 0.5, which is the good scaling, then we have an output which is close, which is fine, which is around 0. Sorry, around 1, not 0, sorry, it's around 1. When beta is too small, then it's very bad in the sense that we have the explosion zone. And when beta is too large, that's what we already know, then we have just the identity regime. So it's it's becoming extremely small. So the good situation is there. The same thing happens there for a regularity of 1, smooth regularity. We know that the good scaling is 1, it's fine, and the black zone is there. If beta is too large, then we have the identity regime, and when beta is too small, we have the explosion regime. And we see that we have a bunch of intermediary situations there where the good situation, I mean the black situation, seems to happen for a scaling equals to the regularity. And the regularity is the Hurst index. So that's the Hurst index. We have no proof of that, but this means that you can, in fact, initialize a ResNet with any type of distribution on the weights, provided you tune the scaling, you implement the scaling, which is in accordance with the process that you use for initialization. So that's very, very interesting. And there seems to be some kind of saturation there. And it's essentially for what? But anyhow, we would like to prove that we have this sort of continuity between the two regimes. Okay, so that's the more prospective part of this presentation. We have clean proof for this regime, clean proof for this regime, just speculation about what's going there. Now, maybe in the last 10 minutes, I will tell you some words about the learning process, because up to now, I've only spoken about what happens at initialization. I mean, I had this network, I put random weights on it, and I was looking at the output. Of course, this is interesting, but what really matters is what happens during the training of networks. And how do you train in neural networks? Well, you perform gradient descent over the space of parameters using the data. over the empirical risk in order to find the best parameter. And of course, then you may ask, but if I use at the beginning of my networks the distribution over the weights, can we follow the distribution of all these weights during the iterations of the gradient descent? It's very hard. It's very hard, of course, because everything becomes dependent. And there is a dynamic which is very complicated. And so we have no idea for now, in full generality, of the way the weights behave during the gradient descent. And of course, it's a very important information that we would love to have, because knowing the type of the distribution that you have after training, of course, could help understanding the type of minima that you get, where you should look for in order to better optimize your network, etc. So that's full of information, but of course, it's hard. And I mean, there is still a lot of research to be done on this. What we can do is experiences. And so look, here, that's an ID initialization. Here, I'm just following a weight at initialization, which is initialized using the ID case. So everything is random. So I'm following the value of a weight, of a random weight, when I have 1,000 layers. Then I use this initialization. I perform my gradient descent, and I look at the distribution of, well, at the value of my weight after training. You see that here seems that so that's the that after training, I mean, that's the optimal parameter, and you see it seems to be ID distributed again. Interesting, but many other situations are possible. In fact, for example, if I initialize my neural network again with random weight, but this time I take a scaling which is larger than 1. Then I have a distribution of the weights which look much more smoother, and which is interesting. So there is a signal, and that's smooth. So does that mean that in the end, after training, that I pass from a stochastic differential equation to a differential equation? So that will mean that the gradient descent is sort of stabilizing my neural network from distributional point of view. I have no idea, but that's of course an interesting route for research. The same thing happens if you use a smooth initialization. So ODE regime. So I use a smooth initialization of my networks and that's typically the kind of curve. So again, that's a weight which is followed over the layers. The kind of distribution that you end up with after training, and you see that there is still some regularity of the weights. It does something. So is it an ordinary differential equation? How do we pass from this differential equation to these differential equations after gradient descent? That's the challenging issue, of course. So the conclusion is that, it's a practical conclusion, that the weights after training still exhibit very strong structures as functions of the layer. And their regularity is clearly influenced by both the initialization, I mean, the type of initialization that we took, very regular versus ID, and the choice of beta, the choice of the scaling. And so playing on these two parameters could really help understanding the landscape, the distributional landscape of the optima after training. And in terms of performance, and that will be my last slide, that's also very, very interesting. So here, what we did is that I did exactly the same protocol as before. So that's fractional Brownian motion there. So H is the regularity. So again, here that's the ID regular, that's the ID initialization, and here that's a smooth initialization. And then otherwise, I initialize my network with the increments of a fractional Brownian motion with this H as parameter. So it's extremely easy to do. And then these are here the scaling. And that's for the MNIST dataset, and that's for the CIFAR10 dataset. And so what does that mean here? Each pixel, it's a pair of scaling regularity. So I initialize my network with this pair regularity scaling, and I do the gradient descent, and I look in the end how well I predict on a separate test set. And of course, if it's pale or red, it's fine. Otherwise, it's bad. And so we see that if we are in the good zone, I mean, in the RID case, the good zone is 0.5 is there, then we see that we predict well. On the other hand, if beta is too small, well, then of course the prediction is not very good. The quality of the prediction is close to 0, which is very bad. On the other hand, if beta is too large, then there seems to be no clear degradation of the learning process. It's not so clear on CIFAR 10. Of course, we see that when we do this with the regular initialization, then again, everything happens around the good zone 1, 1. It's there. And when beta is too small, then it starts to be less and less good. And otherwise, well, if you initialize with the H, which is between 0, 5, and 1, then again, everything seems to happen around there. And if beta is too small, then you have it means that you have an explosion at the beginning of training and then you pay it after training. So the performance of the network is very bad in terms of classification. Otherwise, it's unclear. If beta is too large, there is not really a clear degradation in learning. So that this zone is very interesting. And I mean, it's unclear what's happening there. I mean, it's when beta is too large. It means that that's when the network at initialization just reproduces the identity. So is it bad or not for learning? Well, the answer is not that clear. So in conclusion of this presentation, the conclusion is that deep limits, they allow to understand scaling and initialization strategies for ResNets. What you should keep in mind is that the standard initialization, the correct scaling is 1/2, not 1. And to train very deep ResNets, it's important to adapt scaling to the weight regularity. So you may want to use RID initialization. In that case, you should use initialization, which is 1/2. You may want to use much regular initialization. In that case, you have to adapt the beta. So there is a very strong interplay. Then, of course, the question is, what about training? What about the performance after training? Well, we have no results on this. And of course, the good question is also, how should we choose the regularity of initialization for a given problem? Because you could tell me, well, initialize your network with ID observation is fine. Okay, it's fine. But you may imagine that you could change the distribution of the initialization if you want to enforce some particular zone in your network. How is the choice of initialization connected to your learning problem I think it's a very important issue, but we have no answer to this question for now. And if you want to know more, this paper is on arXiv website. So that's all, and I thank you very much for your patience and your attention.
Okay, thank you, Professor Biau, for your excellent presentation. I mean, it's an extremely technical and mathematical material, and Professor Biau has made a commendable effort in making the things understandable in an online presentation. I mean, it's quite impressive. Okay, so I learned a few things today which I didn't know about. Now, Professor Biau, there are a few questions for you on the chat box. Are you able to see them? First one is from Anand Shah.
Just wait 1 second, please.
Yeah, sure.
Okay, I can hear. It's fine. Yep.
Yeah. So
okay.
The first question is from Anand Shah.
Hi. In this approach, initialization also applicable to other architecture which use residual connection like transformers. Excellent questions. Excellent question. Of course. Or is it specific to ResNet and its variants? Thanks. No, it's not at all irrelevant. It's not a naive question at all. It's a very, very good question. And of course, it's the wonderful challenge will be to understand what's happening for transformers that use, of course, this skip connection. But for you to understand, and this skip connection, they have proved with these ResNet style networks to be useful. And then now they are used in transformers, in attention models. They are used in RNN, as I said before. They are used everywhere. And so, of course, understanding the role that it plays in other type of architectures, such as transformers, it's a very, very interesting problem. And connecting stochastic differential equations and transformers for this type of with this connection. It's a very challenging question, and so no, it's not it's a very interesting question. Yeah. Is there any application of PD theory in ResNet? Yes, there are, of course. Yes, there are, because once you have this continuous point of view, then you can use solvers of differential equations in order to implement these solvers to optimize your network. So yes, yes, there are, and actually this point of view has been a sort of revolution for many practitioners, where they have used these tools in order to propose new architectures, to propose new solving procedures, etc. So yes, they are used. It's not my field. It's much more practical, much more applied, but I can assure you that many people use it. For example, we have here in the computer science lab, the team of Patrick Gallinari. They are working on climate data, and this point of view, the tools that are carried, of course, by this point of view, have been very influential for them. Yeah. So the answer is yeah. Yeah. If I may wonder, with the optimal initialization, sorry, can we model higher order and higher degree differential equation using ResNets? Good question. I have no idea about that. That's a question of crucial both. Can we model higher order, higher degree differential equation using ResNets? Probably. Very good questions. I don't know how. But then you have to transform the architecture, but probably, yeah. If I may add one more, with the optimal initialization, how does it impact the training time to convergence, apart from avoiding gradient explosion or vanishing? I think there is no clear impact on the gradient on the training time. I'm not sure of that, Anand, but I would say that there is no impact. I'm not sure. There is a confidence interval by my answer, but I think that does not impact. Not sure. Nirjan Motion Shiva, thanks for the talk. Thank you very much. Are there any constraints on the loss function with respect to prior knowledge initialization of weights? No, in fact, there is no constraint on the loss function with respect to prior knowledge initialization. No, there is nothing. In fact, well, we assume that the loss is differentiable, of course, because we with respect to the hidden space for the gradient, but that's all. That's all, because we have no results in generalization or whatever. So no, there is nothing particular on the loss. Question of quota. For a critical beta, the variance of the norm seems to be high. What does it happen? Is it verified in the theorem? The variance for critical beta, the variance of the norm seems to be, and is that in the theorem? Also, if the initialization change to different distributions, say uniform, how does the beta change? Very interesting questions. All these questions are very nice. It's a very challenging question. So information about the variance with respect to beta, I don't know, because I do not have the final distribution, and that's a very good question. That's the histogram that I show in my presentation. So unfortunately, I cannot answer to this question because I have no information for now regarding the final distribution. So Kota, I'm really sorry, but that's a good question, but I'm not able to answer this question. And also, if the initialization is changed to uniform distribution, say uniform, how does beta change? So beta does not change because uniform distribution works fine. It's sub-Gaussian. What is going to change is, of course, so it's a sub-Gaussian distribution with a parameter of sub-Gaussianity, which is different, of course, from a Gaussian distribution. And then it's going to change the form of the final distribution, and probably that's connected to your question, the variance of the final distribution. And so, since I have no information regarding the form of the final distribution, that's the same answer as before. I cannot unfortunately answer the question, but that's you really got the idea. Why we are using gradient descent algorithm only and not other optimizers such as Adam optimizer? Of course, I'm saying gradient descent, but that's including Adam, etc. And what is the intuition behind training searchline network without any dropout in the hidden layer? Well, I have no intuition about that. No. I can't answer this question. I understand the question. I perfectly understand the question, but the connection between why don't we use dropout in the end and what does that work? Of course, if you introduce dropout, dropout is more, it's a trick that I'm not studying in this presentation. Of course, that's going to help in learning. Well, I don't know. I would love to answer you, but what is the intuition behind training such and without any dropout in the hidden layer? Why is it better using dropout? Why is it work? Why is it the same without using dropout? I have no intuition about that. I'm sorry. But all these questions, they are very, very fine. You were very attentive. Huh? Excellent.
Okay. Thank you, Professor Biau, for attending all those questions. Now it's over to Anish.
Another question in mind. So in your slide, you showed that the expected norm difference between the capital HK by L and small hk, that is upper bounded by a universal constant C divided by root L in the regular regime and L in the smoother regime. And the square root and the power of L actually determines the value of beta, that optimum phase transition beta. So if the width, the value of D, I think it is hidden somewhere in the universal constancy. So the basic assumption that you are basing, the foundation of your theorem is that the D is kept constant, right? So, but also we can change the D, right? Because in terms of L, we can just, so is there an intuition behind? So
I have no excellent question, Anish. And of course, in practice, people will change the value of D because the network will have different dimensions. And of course, everything is getting much more complicated because in that case, well, the dimension of the equation is just varying over the layers. And no, we do not know for now how to do. We don't. So maybe you could imagine a lower equation with the maximal D, with a small. Sorry, you could imagine a upper and a lower bound on the equations.
Right. So the maximum of the intermediate.
Exactly. But I'm not even sure of what I'm saying. So that's a very, very good point. Yeah, very good point. That's a strong assumption on my presentation that the value of D is kept fixed. And of course, this is for having the structure of an equation of a differential equation over time. Yeah.
Right. Thank you. So another question there might be, because while calculating the gradients, you had this equation in place that some small q sub qkz equals to delta hk by delta h naught times z, if I'm clear with the same. So if hk's are the sequential gradients in the hidden layers, and if they kind of vanish or explode, this equation might actually fall apart, right? So does this gradient calculation also gets affected by vanishing gradients or exploding gradients?
Probably yes. Yeah. Not sure of that, but that you're perfectly right again. Yeah, that's correct.
Okay. So thank you so much.
Thank you very much.
So, okay, sir. So Professor Choudhury, you want to?
Okay, so let's thank Professor Biau for his excellent presentation and also the audience for very interesting questions. Yes, Professor Biau, you want to say something?
Yeah. May I make an announcement?
Yeah, sure.
Okay, fine. Then because I know there are many students in the room, and so we have a PhD program in my center, so that I would like to advise. Is that possible?
Sure.
Sure. So I have to share my screen again.
Yeah, sure.
So just 1 second. So it's there. Do you see my screen?
Yes.
So it's there. So here. So please, so that's a very important European program that we have won last year. It's called Sound.ai. So we have 30 PhD positions for foreign students only, not for French students, for excellent students from all around the world. So we have 15 positions this year and 15 positions next year. And so if you students or the students who are in the room are looking for a PhD in Paris, so please consider applying to this program. So for this year, it's still open until the end of the month. So you still have 2 weeks to candidate. So that's very easy, and you have the projects are on the web, so are on the Sound.ai website. So you see the projects there. So you have some are applied, some are in computer science field, some are in math, etc. So we have approximately 30 projects. And so if you are interested, just apply. We will offer 15 positions this year and 15 next year. So if you consider doing a PhD in Paris, so of course then you get a grant, etc. So that's a very interesting European program for attracting talents from everywhere in the world. Not so that the French students, they cannot apply to this program. So it's called sound.ai. Is that okay?
Yes.
Thank you. Thank you for the information.
And then the last step, maybe look, I want to show Paris. Just say hello from Paris.
Oh, excellent.
Can you see?
Yes.
So I have a very nice view from my apartment. So you see the Eiffel Tower.
Okay.
And that's my university here that you can see with the tower, the Jussieu Tower. Maybe some of you may know. And you see the weather is very nice today in Paris.
Thank you so much. That's beautiful. Yeah.
That was a gift for the students.
Okay.
Have a nice day. Thank you again for having me today.
Thank you. So Anish, I think we are closing the session now, right?
Yes, sir. Thank you so much. Thank you everyone for joining.
Yes. Bye to the students.
Okay.
So with that note, I think I'll conclude the session. Thank you all for joining and being patient with and again, thanks Professor Gérard Biau for attending and Professor Prof for giving us your precious time. So thank you so much for the entire team of WSDL 2023. Thank you.
Bye-bye, everyone.